There is a powerful urge in science, and in human thinking generally, to seek simplicity. We want our theories to be elegant, our explanations straightforward, our pictures of reality clear and uncomplicated. This drive towards simplicity has served us well in many ways, leading to beautiful unifying principles and powerful generalizations. But I must tell you something that has become increasingly clear to me through decades of working with quantum mechanics. The pursuit of simplicity can be deeply misleading, particularly when we try to understand the atomic world. Reality at the quantum level is not simple in the ways we would like it to be, and our insistence on forcing it into simple conceptual frameworks often leads us astray. Understanding why simplicity misleads us, and learning to embrace the necessary complexity of nature, is essential for truly grasping quantum mechanics. Let me begin with my own early work, which illustrates how the desire for simplicity shaped and limited my thinking. When I developed my atomic model in 1913, I was trying to make sense of how electrons could orbit a nucleus without radiating energy and collapsing, as classical electromagnetism predicted they must. I proposed a simple solution: electrons could only occupy certain discrete orbits, and while in these special orbits, they would not radiate despite being accelerated. This was appealingly simple. It gave me discrete energy levels that matched the observed spectral lines of hydrogen beautifully. But this simplicity was misleading in important ways. By talking about electron orbits, I was encouraging people to imagine electrons as little balls following definite circular or elliptical paths, just like planets around the Sun, only smaller and with quantum restrictions. This was a simple picture, easy to visualize, and it helped many people grasp the basic idea of quantized energy levels. But it was fundamentally wrong about what electrons are and how they behave. Electrons do not follow definite trajectories. They do not have precise positions and velocities simultaneously. The simple planetary picture, for all its pedagogical utility, misled people about the nature of atomic reality. As quantum mechanics developed through the 1920s, it became clear that any simple picture of atoms was inadequate. Erwin Schrödinger showed that electrons must be described by wave functions, mathematical objects that spread through space and give probabilities rather than definite positions. Werner Heisenberg showed that position and momentum cannot both have precise values simultaneously. The simple idea that electrons are particles following paths had to be abandoned, but so did the simple idea that they are waves in the ordinary sense. They are quantum objects that sometimes behave like particles and sometimes like waves, depending on how we observe them, and neither simple classical concept captures their full nature. This is where the concept of complementarity, which I developed, becomes crucial. I argued that we need both particle and wave descriptions to fully understand quantum objects, but these descriptions are complementary rather than unified in a single simple picture. In experiments designed to reveal particle properties, electrons behave as particles. In experiments designed to reveal wave properties, electrons behave as waves. Both descriptions are necessary, both are true in their contexts, but they cannot be combined into one simple, coherent classical picture that works in all situations. This complementarity means giving up on a kind of simplicity that physics had traditionally sought, the simplicity of a single unified description that captures all aspects of a phenomenon simultaneously. Instead, we must work with multiple complementary descriptions, understanding when each applies and accepting that they cannot be merged into something simpler. This is more complex conceptually, but it is the only way to be faithful to how nature actually behaves at the quantum level. The pursuit of simplicity also misleads us about the role of measurement in quantum mechanics. In classical physics, measurement is conceptually simple. Objects have definite properties whether we measure them or not. And measurement simply reveals these pre-existing properties. The conceptual picture is clean and straightforward. But quantum mechanics shows us that this simple picture is wrong. Measurement does not merely reveal pre-existing properties. It plays an active role in bringing properties into definite existence from quantum indefiniteness. The wave function, which describes a superposition of possibilities before measurement, collapses to a single definite outcome when measurement occurs. This is far more complex than the classical picture. We must now distinguish between the quantum state before measurement and the classical outcome after measurement. We must understand that different properties are complementary and cannot all be made definite simultaneously. We must recognize that what we observe depends on how we choose to measure, on the experimental arrangement we set up. The simplicity of the classical picture of measurement, appealing as it is, misleads us about what actually happens when we observe quantum systems. Albert Einstein was deeply committed to simplicity in physics. He believed that the ultimate goal was to find simple, elegant laws that described everything, that reality should have a simple underlying structure even if we had not yet discovered it. When he looked at quantum mechanics with its complementarity, its measurement-dependent properties, its irreducible randomness, he saw complexity and confusion rather than truth. He thought that quantum mechanics must be incomplete, that there must be simpler hidden variables underneath that would restore the kind of simple, deterministic picture that classical physics had provided. Einstein's famous declaration that God does not play dice with the universe was a statement of his faith in simplicity. He believed nature must operate according to simple deterministic laws, not probabilistic ones. The complexity and apparent randomness of quantum mechanics was, to his mind, evidence that the theory had not yet reached the simple truth underlying atomic phenomena. I understood Einstein's desire for simplicity. Who would not prefer a simple, elegant, deterministic theory to a complex, complementary, probabilistic one? But nature is not obliged to conform to our aesthetic preferences. The question is not what kind of theory we would like but what kind of theory matches reality. Experiments testing Bell's inequalities have shown definitively that Einstein's hope for simple hidden variables was misplaced. Nature really is probabilistic at the quantum level. Properties really do not all have definite values independent of measurement. The simple classical picture that Einstein sought cannot be reconciled with experimental results. The complexity of quantum mechanics, uncomfortable as it may be, is the complexity of nature herself, not an artifact of incomplete understanding. The double-slit experiment provides a perfect example of how simplicity misleads us. The setup seems simple enough: send electrons through two slits and observe where they hit a screen. But understanding what happens requires abandoning simple classical thinking. If we do not observe which slit each electron goes through, we see an interference pattern that can only be explained if each electron somehow goes through both slits simultaneously, like a wave. If we do observe which slit each electron goes through, the interference pattern disappears and we see two simple bands as if electrons are particles going through one slit or the other. The simple question which slit did the electron go through turns out to have no simple answer when we are not observing the path. The electron did not go through the left slit or the right slit. It was in a quantum superposition of both possibilities. This is not a simple classical state that we can easily visualize. It is something fundamentally quantum that resists simple description. Any attempt to simplify it, to say the electron really went through one slit or the other, and we just do not know which, leads to predictions that contradict experimental observations. The pursuit of simplicity also misleads us in how we think about causality in quantum mechanics. Classical causality is appealingly simple: causes produce effects in a deterministic chain, and if we know the complete state now, we can predict the future state with certainty. But quantum mechanics introduces fundamental randomness. When a radioactive atom decays, there is no simple cause that determines the exact moment of decay. The timing is irreducibly random within the constraints of probabilistic laws. We can give the probability of decay per unit time, but we cannot point to a simple causal chain that made this particular atom decay at this particular moment. Some physicists find this so unsatisfying that they propose hidden variable theories that restore simple deterministic causality. But these theories must introduce elaborate non-local mechanisms to match quantum predictions, and they have not proven more useful or illuminating than standard quantum mechanics. The apparent simplicity of deterministic causality is purchased at the cost of hidden complexity elsewhere. Nature seems to prefer genuine probabilistic laws at the quantum level, and accepting this, rather than seeking a simpler deterministic picture underneath, appears to be the more honest and productive approach. The wave function itself illustrates the tension between simplicity and accuracy. In a sense, the wave function is a beautifully simple object. It is a single mathematical function that contains all the information about a quantum system and evolves according to a simple, elegant equation, the Schrödinger equation. But what this simple mathematical object represents is far from simple. It gives probabilities for measurement outcomes. It exists in an abstract multidimensional space, not an ordinary three-dimensional space. It cannot be directly observed. And its relationship to classical properties we can measure is complex and mediated through measurement processes. If we seek a simple picture of what the wave function represents physically, we will be misled. It is not a physical wave made of some substance. It is not simply a description of a particle's position. It is a more abstract mathematical structure that encodes quantum possibilities in a way that has no simple classical analog. Trying to force it into simple classical concepts inevitably distorts our understanding. I developed the Copenhagen interpretation of quantum mechanics partly to help physicists avoid being misled by oversimplifications. The interpretation emphasizes complementarity, the role of measurement, the limits on what can be simultaneously known, the contextuality of quantum descriptions. This is more conceptually complex than a simple classical picture where objects have all their properties defined at all times independent of observation. But this complexity is necessary to capture how quantum mechanics actually works and what experiments actually show us. Some critics have said that the Copenhagen interpretation is too complicated, too philosophically dense, too evasive about what is really happening. They want something simpler and more direct. But I would argue that their desire for simplicity is leading them to demand something nature does not provide. Quantum mechanics is subtle and complex because quantum reality is subtle and complex. Our theories must match this complexity if they are to be accurate, even if this makes them less satisfying to our desire for simple pictures. The pursuit of simplicity can also mislead us about what questions are meaningful in quantum mechanics. It seems simple and natural to ask where is the electron when we are not measuring it, or what is its momentum right now, or which path did it take through the apparatus. These are grammatically simple questions that make perfect sense in classical physics. But quantum mechanics shows us that these simple questions often presuppose things that are not true, like that position has a definite value independent of measurement, or that momentum and position can both be precise simultaneously. Learning which questions are meaningful and which are based on misleading classical simplifications is part of the art of understanding quantum mechanics. We cannot simply import all our classical questions and expect simple answers. We must learn to ask quantum questions, questions that respect complementarity and uncertainty and the role of measurement. This is more difficult than sticking with simple classical questions, but it is necessary for avoiding conceptual confusion. There is also a sense in which the mathematics of quantum mechanics is deceptively simple. The Schrödinger equation itself is quite elegant, a partial differential equation similar to wave equations in classical physics. The rules for calculating probabilities from wave functions are straightforward. The formalism is teachable and usable without tremendous mathematical sophistication. But this mathematical simplicity can mislead students into thinking they understand quantum mechanics when they have only learned how to calculate. The calculations are relatively simple, but understanding what they mean, what kind of reality they describe, what philosophical implications they have, this is far from simple. I have seen many students who could solve quantum mechanics problems with facility but had not grappled with the conceptual difficulties, the questions about measurement and reality and complementarity that make quantum mechanics truly challenging. They were misled by the simplicity of the mathematics into thinking the physics was equally simple. Only when they started asking deeper questions about what the formalism means did they discover the complexity that lies beneath the mathematical surface. The history of physics shows a pattern of initial simplifications giving way to necessary complications. Newton's laws seemed wonderfully simple, describing all motion with a few equations. But then we discovered they were approximations valid only at speeds much less than light. Einstein's relativity added complexity, showing that space and time are intertwined, that simultaneity is relative, that mass and energy are equivalent. This was more complex than Newtonian mechanics, but it was also more accurate and more general. Similarly, classical physics seemed simple and complete until we probed the atomic realm and discovered quantum mechanics with all its conceptual complexity. Perhaps we will discover that quantum mechanics itself is an approximation to something even more complex and subtle. The lesson seems to be that simplicity, while aesthetically appealing, is often a feature of our limited understanding or restricted domain of application rather than a fundamental characteristic of nature. This does not mean we should abandon the search for simple principles. Unification and simplification are valuable goals in physics. Finding that electricity and magnetism are aspects of a single electromagnetic field was a great simplification. Finding that quantum mechanics and relativity both emerge from quantum field theory is another. But these unifications often reveal that the simple picture we had before was an approximation, and the unified picture, while simpler in some respects, is more complex in others. The key is to distinguish between mathematical elegance, which is genuinely valuable and often a sign we are on the right track, and conceptual simplicity in the sense of easy visualization or direct mapping to everyday experience, which can be misleading when we are dealing with phenomena far removed from ordinary scales and conditions. Quantum mechanics has mathematical elegance in its fundamental equations, but it does not have conceptual simplicity in the sense of being easily picturable or intuitively obvious. I think the reason simplicity misleads us is that we evolved to understand the macroscopic world where quantum effects are negligible and classical physics is an excellent approximation. Our cognitive apparatus, our intuitions, our natural ways of thinking are all adapted to this classical domain. When we encounter genuinely quantum phenomena, our instinct is to try to understand them in simple classical terms, using concepts like particles and trajectories that make intuitive sense to us. But these simple classical concepts do not accurately describe quantum reality, and clinging to them prevents us from understanding what is actually happening. Learning to think quantum, to accept complementarity and superposition and measurement dependence as fundamental features rather than complications to be eliminated, requires overcoming our natural preference for simple classical pictures. It requires intellectual discipline and willingness to work with concepts that feel strange and unfamiliar. It requires accepting that nature at the quantum level is simply not as simple as our everyday experience would lead us to expect. When students or colleagues ask me how to develop better intuition for quantum mechanics, I tell them that they should not try to force quantum phenomena into simple classical pictures. Instead, they should work extensively with the mathematics, solve many problems, study many experimental results, and gradually develop a quantum intuition that is native to the quantum domain rather than borrowed from classical physics. This quantum intuition will never feel as simple or natural as classical intuition because our brains are not wired for it, but it can become familiar and usable through sustained engagement. The pursuit of simplicity has given us many of the great advances in physics, but it has also led us astray when we insisted that reality must conform to our desire for simple pictures. Quantum mechanics teaches us that nature is under no obligation to be simple in the ways we would prefer. She has her own structure, her own logic, her own way of being that we must learn to understand on its own terms rather than forcing into preconceived simple frameworks. Why does simplicity mislead us? Because it encourages us to think that reality must match our preferences, that nature should be easily visualizable and intuitively graspable, that complex phenomena can always be reduced to simple underlying mechanisms. But quantum mechanics shows us that this is not how nature works at the atomic level. The complexity of quantum mechanics, with its complementarity and uncertainty and measurement dependence, is not a sign of incomplete understanding but an accurate reflection of the genuine complexity of quantum reality. And accepting this complexity, working with it rather than trying to eliminate it through false simplifications, is the path to true understanding of the quantum world.